I am very happy for this opportunity to introduce you all to our company, SHUTE Sensing Solutions, our technology and some of our products. So my name is Kristian Nielsen. I am the CTO of the company and one of the founders. And I have a background from the Technical University of Denmark. And SHUTE Sensing Solutions is also a spin-out from the Technical University of Denmark. We never moved far away from home because we are now located only 30 minutes north of Copenhagen. We're a small company. We like to think of ourselves as a mature startup. And here's a family photo of us. And it can be hard for me to believe, but next week we will turn 10 years old. And with that, we have been on a journey from taking our technology from the lab to now offering it to multiple industries. So let me talk a little bit about our technology first. So we do polymer optical fibers, and with them we can offer a sensor that is very sensitive to stress and has a very large strain range. It can measure humidity and it can measure temperature. And from those three parameters, we get our name, which is strain, humidity, and temperature. And yeah, being around for 10 years, we've also been able to demonstrate our technology in many industries. So we think of it as a fairly well-established technology. We've applied it in the construction industry, in medtech industry, and in energy industry. I'll get a little bit back to that in a minute. Further on our technology, we make our fibers out of polymer, but we use the microstructured fabrication technique. And as you can see in the top left corner, there's a scanning electron image of the end facet of the fiber. We have 36 holes running through the length of the fiber in a lattice arrangement, and in the center there's a hole missing, and there where the hole is missing, that's the core of our fiber, and that's where we capture light. So using microstructured or photonic crystal technology like this enables us to make our fibers single mode. It also makes it possible to make fibers without any doping. So we can use pretty much any polymer. Our only requirement is that it's a thermoplastic and it's fairly transparent. We manufacture all of our fibers in-house. We use the drill and draw method, where we use a CNC machine to drill the holes in the pattern that we require. And then we have two draw towers to stack or to scale the fiber down from a 60 millimeter preform down to a hair thin fiber or any dimensions that we want. Well, this fabrication technique was developed at university, so there's nothing new there. Our mission has been to take this technology from the lab and make it mature enough to go into industry. And two of the biggest barriers that we identified early on was the handling of the fibers and the cost of instruments. Now, the handling of fibers involves simple things such as putting a connector onto the fiber, putting protection and housing and adhesive methods or barriers for moisture or other handling mechanical aspects. And this, of course, is continuously going on. The other aspect is the cost of instrument. Our sensing system is based on fiber Bragg ratings. So in our polymer fibers, we will use the UV laser and a face mask to write fiber Bragg ratings into distinct points along the fiber. Each fiber Bragg rating is a sensing element, and the unique property of fiber Bragg ratings is that you can put many FGBs on the same fiber, so you can have a whole series of sensors on a single strand. Now, in order to interrogate these fiber Bragg ratings, you need a light source and a spectrometer. And part of our mission has been to lower the costs of these instruments. And our latest contrast system is now down to 2,000 euros. And I think that this is a very interesting problem. And I know that there are other companies working on this as well. So I look forward to actually getting that cost down. Because the lower the cost of the instrument is, the more markets we can address, the more applications we can address with our technology. Now, the sensors themselves, being made of polymer with a FGB in them, really enable us to utilize the benefits of polymer optical fibers, such that in the sense that the polymer can be, the polymer is much more soft than a glass fiber. Glass fibers are notoriously very stiff and hard to work with, and they break in a sharing method, whereas polymer fibers are much more flexible and can be more easily stretched and have a different failure mode. The low Young's module of polymer fibers makes them ideal for picking up very small stress levels and also makes them compatible with soft materials. So we have some applications where we embed our fibers into rubbers or into carbon fiber elements, plates. And in that sense, we offer new optical strain gauge capabilities to places where you maybe couldn't go with glass fibers because of their inherent strength. On top of strain sensing, our fibers have a lot of traction as humidity sensors, which is also a fairly unique capability to polymer fibers, because they are some polymer fibers are inherently absorbent of humidity, and that makes them very good as humidity sensors. We have our own sensing system for that we have developed called CongDry, but we've also seen a pull for making optical sensors that are compatible with C-band equipment. And these kind of sensors we see as a complement to silica fibers, to glass fiber sensors, such that you could have a daisy chain of silica fibers, and at the end you could have one of our polymer fiber sensors as a humidity sensor. We have the big advantage of using the polymer fibers as humidity sensors is that they are much more robust with regards to very high humidity levels. We can leave them in water for months, and afterwards they will still function after they dried off. There's no drift and there's no lock-in problems, as you might see with the electronic humidity sensors. And they are fairly compatible with many harsh environments. And yeah, being made of polymer, the sensors themselves, they do not corrode and they do not conduct electricity. We have a few applications running with these kind of humidity sensors, and we have envisioned them being used in structural health monitoring, but also for critical infrastructure on pipelines or in tunnels, where you want to make sure that there's no ingress of moisture. They can, of course, be customized to different kinds of housings and different kinds of membranes that you can put onto them. The last thing that I would like to mention is that we are also offering chirped fiber bag gratings. These chirped fiber bag gratings are a fairly novel technology from our side, where we can make up to 100 millimeter long chirped FGBs. And these offer unique properties when it comes to detecting fast events, such as detonation fronts or shock waves in materials. And again, we utilize the unique properties of polymers, being that they have a much lower mechanical mismatch with as compared to glass fibers. But this technology has already been demonstrated by the nuclear research facility in France, SEA, where they've done shock wave detection using our fibers, where we're basically using the polymer optical fiber and basically the destruction of the fiber for timing the arrival of the detonation waves. And then this kind of technology has a lot of promise, as well as maybe in other kinds of structural health monitoring, as in small solid rocket motors and stuff like that. I think with that, I will finish my small presentation. I look forward to your questions.